Good afternoon, everybody. Let's go ahead and get started with today's webinar. So first off, my name is Derek Schrader, working for GROB Systems based out of Bluffton, Ohio. I'm leading the team, our sales team and our application team for our universal machine sales. So today we've partnered with OpenMind and Walter Tools, and we'll go over a demo and some key highlights about knee prosthesis machining. So the format today will be roughly a 1 hour webinar. At first, we'll do a real brief company intros, just for those of you who don't know who we are. Then we'll get into some demo info, some technical highlights, and a video at the end. And also at the end, we'll have a question and answer session. So if you have any questions along the way, please type them into the chat box, and we will get to as many as we can within the hour. So with that, let's go ahead and get started. So for those of you who don't know GROB, we're a German-based company, still family-owned. We have 5 production plants around the world. In the U.S., we have a plant in Bluffton, Ohio, where we have close to 600 employees. So we've started in Bluffton in the early 80s. At the beginning, it was a small sales and service office, and we've grown through the years to where we are today, which is a full manufacturing site that builds our complete product, all of our product lines that the GROB company offers. So here you can see the overhead view of GROB Bluffton. So it all starts off with sales and engineering. So when we get into projects where we require specialized solutions, which is really what we're known for, that's where it all starts in engineering. We have a staff of mechanical engineers, fluids, electrical, software, who all get the project started. Then out into the plant, we have a full production facility, which is actually fed by our apprenticeship department, which has been in place since the beginning. So we actually had one of our biggest classes about 2 years ago with 40 apprentices in a single year. So in our production facilities, we're doing all machining, fabrication, painting, so everything from the machine from the start to the end, including assembly. We have an application center. For those of you who are in the medical industry, we realize the long process it takes to get through that verification process, and we have application engineers in Bluffton to support that process. We also have a service team who knows our machines very well. They've built our machines from start to finish, and we recently expanded our spindle rebuild facility in Bluffton. So briefly about our different product lines. So our traditional heritage is system machining line. So this is mainly for customers in the truck, tractor, automobile business, mainly powertrain components or suspension components, where they come to us and say, we need X number of parts per year, usually in the tens of thousands to hundreds of thousands of parts per year. We design the complete system from the machines, which can be double spindle or single spindle, any special purpose machines, automation, the turnkey down to the fixtures, the tooling. We will engineer and design all of that. And that really goes into our next product line, which is our assembly technology. So typically, if you can machine a head or a block, you can assemble it. So very engineering heavy product line that we support our customers with. And then recently, we've been getting a lot of inquiries and projects in the e-mobility business. So what that means for us is anytime you have a rotor or stator assembly, battery pack, in the past, it was a very manual solution to make these parts. And where GROB comes in is the automation to do it in a high production fashion. So we'll do all the automation for that. And then our main topic today is our universal machines, which is our 5-axis line. And actually the one we're using today is a G150, which was recently introduced late last year. And within that universal machine line, we have different automation solutions and also mill turn machines.
Hello everyone, my name is Ernie Dickinson and I'll be walking you through the CAD/CAM portion of today's project. So before we get into the technical details, I want to talk a little bit about who we are and where we come from. So Open Mind, the developer of Hypermill, based in a town called Wessling, just outside of Munich, founded in 1994. Over 350 employees working for the company. Globally, we have 25,000 licenses and 9,000 customers. Together, we have 16 direct country offices servicing our customers. And where we don't have those offices, we also have dealers and partners to work with our customers there. Here in the United States, we also started in 1996. We take care of the United States, Canada, Mexico, Venezuela, and Colombia. We are direct with our customers. So in most cases, no dealer, so direct support. Our staff is decentralized, mostly so we can be closer to our customers and also our partners. So here's our group. Many different people with vast amounts of experience. The one thing we all do have in common is machining experience. So that ties us together, and we use that to help our customers in any way we can. So how do we look at our product? Well, as you can see here in this graphic, 5-axis is sort of the top of the mountain for us. We sort of push forward with that, and then sometimes backfill our technology from there. Of course, we need a strong base, and that base is a good 2D solution, as well as 3+2 and 3-axis machining. And below that, that's all held together by a strong tool database, the tool builder, very powerful post processors, and very powerful simulation. To the right, you see some of our specialty solutions. These can help specific customers with more vertical markets for anything between aerospace engine work, tire mold machining, and even automation. So we use these tools to service many markets. As I stated earlier, aerospace, both structural and engine components, medical, which we're looking at today, mold and die and general machining. All these markets are in our portfolio of customers.
Hello, everyone. My name is Jamie Betcher. I'm the Business Development Manager responsible for the medical market. I would like to take a few minutes and introduce you to Walter and the engineering competence that we have to offer. Walter was founded in 1919 in Germany by Richard Walter, who was the co-developer of carbide and the inventor of the first CNC grinding machine. You may know some of our competence brands, Titex, Prototype, and Valinite. We have over 3,500 employees across the globe. We service customers in over 80 countries out of 10 production sites and 27 sales offices. Our U.S. headquarters is in Waukesha, Wisconsin, and our U.S. production facility is in Cleveland. Comprehensive range of precision tooling for milling, drilling, and threading, as well as offering services like reconditioning and digital solutions like Walter GPS. We can select a tool from you after inputting a few parameters. We currently offer over 45,000 standard light items, with more than 40% of our products developed in the last 5 years. We can also provide specially designed tooling to fit your needs with 50,000 special line items. Walter works together with its customers to develop tailored solutions for the complete machining of your components. The machining process you'll see today was developed by Walter for the maximum rate of metal removal rate and reduced cycle time. We also provided all the tooling you'll see today. We do not only specialize in unique components, but we can also test and run your components on our on-site at our technology center in Wisconsin. You can be there and experience firsthand how we develop and test individual solutions for the products that you are producing. We can also offer remote engineering support with our networked intelligent factory that stimulates real-world conditions. We also host training sessions and events. We offer our employees, customers, and channel partners technical training, workshops, and group sessions. With our production solutions, we are the ideal partner for planning new manufacturing processes or optimizing your existing one. During the optimization process, we review the clamping systems, the CAM program, and provide you with the best possible tools for the operation.
So let's get into the demo for today. So we're using a G150, so the smallest GROB universal machine. This is a 320 millimeter pallet machine, HSK 63 spindle with 30,000 RPM. So the part information, just some general things. So material is titanium. We're actually starting from block for today's demo, so roughly 3" by 3" by 2". And it does take 2 setups, but we do them both in the part or in the machine at the same time. So first op on the left-hand side and the second op on the right-hand side. And at the end, we'll be able to tab off the finished piece. So real quick about the material. So titanium is used in a lot of different markets, medical and aerospace most notably. So the material is selected in a lot of cases for a couple of reasons: strength to weight ratio, corrosion resistance. We also notice a lot of times it is coming from solid block, especially in aerospace, and it is not the most machinable material that's out there, so it does offer some challenges. So from the machine side, we designed some things to lend very well to machining titanium and these types of parts. We're one being in part accessibility, so we have a large swivel range on our A-axis. So when we have pockets and hard to reach areas, we're able to get to that part. Also, if we have multiple pieces up at once, we're able to do more in a single operation. Surface integrity, so whether it needs to be a high quality surface or something that's for an implant, that is very important. Thermal stability also plays into that, to be able to have a nice surface finish without any blemishes, we need to have a machine which is very stable. And chip evacuation for those areas which are pockets, so we're not recutting the chips and potentially damaging tools.
Every good CAM system needs a powerful CAD system behind it. In this case, the challenge for us was taking a scanned surface, the organic part of the knee, and turning it into something that we can actually machine. In HyperCAD, we use something called global fitting. That allowed us, with one process, to do a couple things. One, it allowed us to realign the UV lines for a better machining pattern. Also, we were able to remove any irregularities in the surface, so we have a nice smooth surface there. These knees, this part of the knee actually rolls as you move your leg. So having the optimum surface was critical in this situation. Also, if these surfaces come in as different patches, global fitting can be used to join them into one continuous machine surface. So our next thing I want to show you is basically how we do this in the software itself. So you can see here the original surface we got from the scanner. It's a little lumpy. This is just natural in most scanned surfaces. We're going to go shapes, global fitting. Simply pick the surface. I'm going to make sure that automatic computation is turned on and keep original as off. I'm going to align the UV lines to the y-axis, and also there's some automatic smoothing further down in the interface there that I'm just going to leave as default. I think
Hi, everyone. My name's Luke Pollack. I'm product manager at Walter US, and I'm going to be just kind of showing you the tools that we used in the application today. The first one you'll see is a high feed mill that we call M5008. You can see it's an indexable design, and it uses a 17-degree lead angle to achieve a high rate of axial chip thinning. This allows us to feed the tool faster and accomplish higher material removal rates. It also directs the cutting forces more in the axial direction in line with the spindle, so it's perfect for long overhangs and long reaches. And the insert allows us to get 4 cutting edges for each insert. We have a couple different geometries available in the insert. The first one, the one we're going to be using today, is F47. You can see it has the more positive rake angle at 14 degrees and just a small T-land up there. The D27 is going to be more of a stronger cutting edge, so resist chipping and abrasive wear, but it does generate a little bit higher cutting force. And to be perfectly honest with you, what we've been finding is most situations, the F47 is more than strong enough so we get a little bit freer cutting with adequate edge protection with the F47 geometry. Here we're looking at our milling grades for either ISO S or ISO M materials. So you can kind of see on the left of the box is yellow for the stainless steel material, and then it starts to shift over to kind of the brown indicating ISO S, either titaniums or even some nickel-based materials like Waspaloy or Haspaloy or Inconel, something like that. They're laid out in actually a hardness to toughness scale. So we actually have wear resistance or hardness of the insert grade in the y-axis and the toughness in the x-axis. So as we move from left to right, we're going from a more hard wear resistant grade to a tougher grade. And the WSP45S over here on the far range of the toughness scale is what we're using today for the titanium material. We actually are introducing a new grade, so we're not using it today. It's pretty new, just within the last few months, and we're going to a new insert milling grade platform called TigerTech Gold. So the insert will be more one uniform color gold, so that helps with easy wear detection. And it's really the next generation of milling grades for Walter. We're seeing huge improvements in tool life, up to and including doubling tool life over our old grade.
Looking at the machine, so from GROB, we have some pretty unique advantages which are not available from other competitors. So one being overhead machining, so being able to flip the table upside down is very advantageous, especially when we start thinking about getting into automation. Being able to keep that work area clean and clear of chips is going to allow for a long unmanned operation. Next is we have a very large swivel range on our A-axis. So on our 350 and larger size machines, actually that A-axis range was 240 degrees, but we can actually get up to 359 degrees on our new 150. And that really makes a difference with being able to do more parts on the table at once, or being able to reach those tough areas on parts that require that. So getting more done in a single operation is the key. Another thing that's unique to GROB is the ability to do the tool change completely out of the work area. So no longer do you have to worry about how large your part is or how long your tool is. The longest and the largest can work together without interference. And our horizontal spindle concept is definitely unique, especially in the G150 size, where in this size machine, GROB is the only one offering a horizontal spindle 5-axis. So looking at the overall machine design itself, so like I said before, we are using a HSK 63 spindle for today. We do also offer HSK 100 on our larger machines. And later this year, we will be coming out with HSK 40 for our G150, which will be over 40,000 RPM. Another thing to keep in mind, especially on these smaller parts, is being able to have a very dynamic machine. We achieve that by having a dual drive on our Y-axis and having direct drives on our A and B. And actually, this was something that we realized throughout the years in close cooperation with OpenMind, is to be able to drive their very dynamic tool paths, we have to have a very dynamic machine. So we had made those changes about 6-7 years ago, along with these guidance with OpenMind. We also have different styles of tables available. So we have mill turntables on the 350 and larger. And we have a dynamic table available on our 350 and soon to be on our 150, which is a smaller size and a quicker speed. We also have a tandem drive on our 350, but this one is geared more towards blade applications in the aerospace industry. So like I said, the G150 is our smallest universal machine, but you can see it's built on the same platform as our larger sizes, which have been out on the market for many years now.
We talked about the indexable high feed mill, the M5008, which is what we're using today, but I also wanted to draw your attention that we also have high feed geometry in a solid version. So if the part is much smaller or you don't have quite the space to run an indexable tool, we have the geometry available in solid carbide. The first one on the left, the MD025, it really offers us the highest performance because it's offered in 2 different grades, which means you can customize the grade selection to the material that you're machining. The gold one would be for carbon steel or cast iron. So it's going to do a very good job resisting the abrasive wear of those materials. And the silver one is more for stainless steel materials. So it's going to be much sharper and do a better job of preventing the material from sticking to the tool. If we do stainless steel directly, we also have what we call an inox flash geometry. And the nice thing about this tool is it's offered with coolant through. So that's not typically standard in a lot of solid carbide end mills. If we're using machining ISO H material, so 50 or 55 Rockwell, we can use the MC089. And if we just need something that's a little bit more universal, the MC025 has a standard titanium aluminum nitride geometry, so you can use the same tool and the same geometry in a wide variety of materials. It's not quite as customized as the first 3 for the application, but it does allow a bigger application range. Another tool that you're going to see quite a bit of today when we actually show the machining video is what we call a 4-flute titanium series. We do have it available in also 5 and 7 flutes, unequal pitch for reducing vibrations, and a wide range of corner radiuses up to and including ball nose configurations. The geometry has an eccentric relief on it, so it kind of teardrops or cams away from the cutting edge. This is going to provide a very strong and stable cutting edge, which we're going to need in titanium machining. If you look in the upper right, though, you can see it's not just for titanium. It has a wide range of materials, high tensile strength steels, even a little bit of stainless steel or cast iron material. Now, it's a little bit tricky because we offer so many different configurations of this tool. We have to kind of manipulate our stocking strategy with this tool. And so it is a standard design. It's a proven design, mostly available as a special order, but with short-term delivery. So basically what that means is we're not stocking every single configuration of the tool. ready for delivery today, but ready for delivery within a few days. That stocking strategy actually allows us to offer even more configurations than what we have already kind of finalized on. So if you need a custom shank, whether it's to help prevent pullout or additional holding, additional length, maybe you need a custom coating for the specific type of material you're machining, or to combat a particular type of failure mode, or even if we have to customize the geometry for what you're doing. Because of the stocking situation, all of those options are available to us, and we can really customize the tool for your specific needs. We offer reconditioning for these tools at the original production facility. That means when we recondition the tool for you, it's reconditioned on the same machine or very similar machine that it was originally produced on, and it gets the exact same coating applied, so you can expect near original condition from the reconditioned tool. Even though it's short-term delivery, we do have a catalog available with all of the standard configurations that we offer, including EDP numbers right in the catalog, so you can easily pick out the configuration of the tool, whether it's 4 flute, 5 flute, 7 flute, the diameter, length of cut, corner radius, and whatever else you need. We do also have in the same brochure a nickel-based series, so 4 and 5 flute tools for nickel-based materials such as stainless steel, or even the other side of ISO-S, Inconels or some other nickel-based material. We're also using a drill today. The one that was selected was A3389 DPL, which we like to call the Extreme Plus. And this is a very, very strong drill. So this drill does not like to be babied or pushed lightly. It likes to see heavy chip loads because it has a very thick web after centering at the point. The amount of material that's there is quite heavy. And so it's very, very strong. But if you push it too light, then it just rubs the material and it doesn't perform the way it should. So we really like to push this drill hard, depending on the size of the drill, maybe as high as 10, 12, even 14 thousandths per revolution. It's offered standard in both 3 times diameter length of cut or depth of cut and 5 times diameter. You can see we have a range of 3 millimeters up to 20 millimeters in diameter, and it does have most of the fractional sizes are offered in within that diameter range. The diameter the tolerance is held to M7, and the shanks are held to an H6 tolerance, so perfect for shrink fit or hydraulic holders or any high performance tool holder.
When we looked at the geometry for the knee implant, it was pretty clear to us that to be the most efficient at keeping the cutting time low, that we had to attack the bearing surface, also known as the condyle surface, with barrel cutters. Cutting it with a ball mill would have just added a huge amount of time to the cutting process. So we were able to use barrel cutters in a way, probably not as traditionally as they've been known for in the last couple of years, and more aerospace type components. We're able to use it on a medical part with very good results. So when talking about barrel cutters, they come in a couple different shapes. If you look on the graphic to the left, there's something called the tangential style, which is the middle tool in that picture. You also have the traditional barrel shape all the way to the right. The problem with both of those types of geometries is you really have a problem with clearance. You can't go as deep as you can into a part without having issues running into the tool holder itself. The only solution to fix this, obviously, is to lengthen the tool, and as we all know, lengthening the tool is not a good solution. So the type of geometry that we prefer here at Open Mind is something known as the conical barrel cutter, where the actual cutting radius isn't tangent to the shank of the tool. It's actually tangent to an angle off the center line of the tool. This actually has two benefits. The obvious one, in reference to what I just spoke about, you have much more tool holder clearance, so you don't have to go to a longer tool. The other benefit is no matter where that contact point is on that radius, the angle of the machine stays consistent, right? So whether you're further up towards the actual shank of the tool or you're actually cutting now down towards the tip of the tool, that angle stays fixed. So less unneeded motion on the machine itself. And barrel cutters come in a couple different shapes themselves. So you have sort of the high angle one on the left for more vertical type situations. This is actually what we used on the knee implant today. You have a more shallow angle for flatter, more horizontal surfaces. And then of course you can have custom shapes. In this case, we're doing a blisk, and if we have too much of an angle on a conical tool, we'll have a situation where we'll run into the adjacent blade of the blisk. So in this situation, a custom shape was adequate for this part. So for us, it's important that not only do we have the right tool paths, but it's also easy to use. And part of being easy to use is we have to make it easy to get the actual cutting geometry into the software itself. So when looking at a barrel cutting solution, it's important that it's parametric, so you don't have to fuss around with custom drawings or bringing in DXF files of the tool. Being able to just simply put in the diameters and the radiuses that come from the tooling manufacturer makes it a whole lot easier and quicker. So part of having a good barrel cutting solution is having control. One thing that we have in the software is the ability to actually adapt the contact point. Having the ability to adapt the contact point gives you a couple of different options. If you look at the picture all the way to the left, it allows you to actually take the tip of the tool and put it into corners, tight areas that you normally wouldn't be able to fit the tool of that size in. Also, you can adjust the contact point as you go through the cut, essentially giving yourself a fresh cutting edge as you go through the whole process. It's actually kind of a unique thing with barrel cutters. So you find, or we found, that using these barrel cutters, you get a really good tool life out of them, and they really last longer than you think they should.
So the Walter tool that we use today is the conical version. We call it MD838. We do also have the tangential version, which we call MD839. And just like one of the other tools we looked at earlier, it's offered in two different grades. So you can really customize the grade of the cutting tool to the material being machined. Again, the gold one would be more for carbon steel, so it's going to be more abrasive resistant, and the silver one is more sharp and preventing material from sticking to the tool. So two different applications. We're showing the solid version of the tool on the screen, but it is also available in a cone fit system, which is a replaceable carbide head that threads onto a steel shank. And this is what Ernie was kind of talking about. The real advantage of the conical or the tangential style tool or the barrel cutter is the ability to reduce the tool paths. So on the left, we're looking at a traditional ball nose tool to finish the part, and you can see we're limited as to the step over based on the diameter of the tool and obviously the surface finish that we're trying to produce. But with the barrel style tool, we can take a much larger step over, reducing our cycle time by up to 90%. And we're already anticipating that due to part configuration, machine capabilities, interferences with fixturing, we're really going to need to customize the tool to the specific application. So we're already set up to custom make any type of tool that you may need, whether it's the barrel style or the lens style or the tangential or conical, and whatever angle of approach you may need to make for your part. we have a system already set up that makes it easy for our either our channel partners or our sales engineer would have to help an end user get a special tool ordered, but the system is already in place.
Taking the contact point control to another level here, Hypermill has something called dynamic contact point control. And what this allows you to do is with a single click of the button inside the software, as you go through a surface, it will actually dynamically change the contact point. You basically give it a start and you give it an end. And as it goes through the process, you get a new contact point. And what you get from that is it's almost like a new cutter every pass as you go through the process. Really good for surface finish, really good for key tool life, obviously, and a very unique solution that's very, very, like I said, very unique situation for a barrel cutter. So here, obviously the more straightforward benefit is the step down. A little bit of a race between a ball mill on your right and the barrel cutter on the left. You can see on the left we're almost done, even though this is sped up a little bit. There's a little side advantage of the barrel cutter where we can actually put the tip into the corner to get blending surfaces in the transitions. We do offer a situation or a technology where we can do it in 3+2, where we break the finishing into 2 separate sides and also do the blending with 5-axis. So you see the time difference in this situation. It's just incredible. And now, just to show you how easy this is, we're going to do it in the software itself. Of course, everything that looks easy is backed up by an incredible amount of math and an incredible amount of technology and thinking. Here, we're showing the interface for selecting the tool, the barrel cutter, everything parametric, like I mentioned earlier. On the strategy tab, we're going to switch to global drive shape. You can see we have some other options there as well. I think the video's stuck. There we go. And then we're going to pick a surface. So we're just going to pick the surface we're going to cut, condyle surface. It's going to realign the UV lines, but we can change that here if we want to go the opposite direction. I can invert the machining side if I want. I have a little graphical representation of the tool, so I know which side we're going to be machining on and which direction we're coming in. Switching the parameters, I can give it a side allowance. I can give it its own semi-finishing path if I want. And the 5-axis, simple and straightforward, just follow the ISO lines. There's several other options there. There's my contact parameter, where I get 20% up the tool. That's how we turn on the dynamic contact point. And also we have an avoid collision option as well. We calculate. And we should get some green lines here showing you the temporary tool path, and then we'll be all linked together. A nice smooth tool path with yellow lines. Since we're climb milling, it's gonna, oh, I guess it didn't finish, sorry.
Sorry about that, Ernie.
That's okay.
Moving on to the machine. So looking at our cross-line Z-axis design, this is also unique for a couple factors. First off, on a GROB machine, the distance from the spindle to the bearing of the Z-axis is always the same since the bearings travel with it. Typically what you see on a vertical is as you come down to the part, you're extending those bearings, which leaves you less rigid. On a GROB machine, you have 3 sets of bearings on the Z-axis. If you compare that to any vertical out there, it's 2 sets, so that's an obvious improvement. And also when we look at when the Z-axis is fully out at the part, it's directly over our X-axis bearings. So the GROB machine, when it's extended, it is the most rigid it can be, which is opposite what you'll see in a vertical is when you're out at the part, you're actually the least rigid you can be. So some other key benefits on a GROB machine is the user efficiency. So Being able to rotate the table upside down, dump the coolant and the chips off is very nice for automation and also for your operators if you're doing a standalone operation. Also, the door opens completely, including the roof, so leaves it open for the crane to come in. And also, if you're going inside, you're not having coolant drips on your head. Also, you can bring the X-axis and Z-axis close to the operator to inspect tools. And also, if you look over on the right-hand side, the tool loading point is right there by the operator, which is in the perfect position.
So the last thing I'm going to talk about today is some tools we have for achieving a high surface quality. The first one is something we call high precision surface mode. Just a little background information. Most CAM systems, whether you know it or not, take apart. They typically create a faceted mesh model on that part. This allows the software to make sure there's no gouges and no gaps between the surfaces. And then the tool path is applied to that mesh model. Of course, the downside is it's faceted, so you're going to see those facets on the surface. Hypermill has some technology built in where we can essentially take the tool path, project it onto the real surfaces, but also check against the faceted model in the background for safety reasons. And this is a very simple solution. Once again, one checkbox, but with a lot of math and technology behind it. So you can see here, the picture on the left actually doesn't look so bad of a surface, but you can see the faceting in the part itself. With our high precision surface mode turned on, you get a part more like the picture in the middle. All the facets are removed, and now the surface finish is solely based on cutting parameters and quality of the tool and quality of the machine and so forth. And once again, in the software itself, very straightforward. Click on high precision mode and it does it in the background. The second technology I want to talk about is our smooth overlap technology. This allows us to take either multiple sections of tool path with the same tool, or maybe even two different tools, or perhaps even a tool in one orientation and another in a second 5-axis orientation. And this allows us to blend between those tool paths. It's not just a simple extension of the tool path. There is an actual blending of the tool path into the adjacent areas. So you can see here in this part, quite a simple part. The one on the left, you can visually see the transition. You may not feel it, but you can see it. Or you may feel it, depends on your machine, I guess. On the one on the right with the smooth transition turned on, it's just one homogeneous surface, no transition at all, very clean. So here in the software, just real quickly, we're going to machine these side surfaces here. So I'm going to new 3D milling profile finishing. I'm going to grab a ball mill. In this case, we're actually going to use a barrel cutter, and we're going to use the tip of the barrel cutter, which is another benefit of a barrel cutter. Really serves two purposes. On the boundary tab, I'm going to pick the surfaces I want to cut. And this is a very quick, simple example. But in there, I can also do a smooth overlap, as we're talking about. There's also an extension option where it visually shows you extensions, but that's not what we're going to do. We actually want the smooth overlap, which will actually roll the edges. So first, we're going to calculate it with it off. And if you zoom up to it, you can see that the tool path goes right to the surfaces we picked, which makes sense. Now we're going to turn the smooth overlap on, recalculate it. And you should be able to clearly see that the tool path now overlaps a certain amount, but it doesn't just go straight off the surface, it actually rolls over the other surface. And there is actually a small transition angle to that as well. So it's not just going on to the other surface, it's really feathering itself to the other surface, which is really nice.
So look at being able to get at all the surfaces of the part. one thing that's critical is the design of the spindle and the table. So having a symmetrical design that allows us to get right up to the part using short tools is critical. Also, if we look at the distance from our center line of rotary to the front of the spindle while the Z-axis is extended, it's a very short distance, around 2 inches on our G150. It's a little larger on the 350, I think about 3 inches. It still gives you a short distance. By the time you add a tool holder in there, you're easily getting past center line even with a short tool. And then here you can obviously see the extended range on the A-axis. So like I said, up to 359 degrees, which allows you to get at those points in a single operation. So surface finish, as Ernie had mentioned, is critical for parts like this. Some features that we incorporate and support that. So we can do all the tool measurements on the machine with a boom laser, and also we can do scanning as well just to verify the tool is what we think it is and make sure it's as accurate as we have in the cam system. We have torque motors on the rotaries. That's going to give you a fast transition and a most accurate transition. There's not going to deal with any backlash issues there. An effective cooling system on the whole machine to overall keep the machine stable and machining a good part all day long. And on top of that, we also offer what we call our high accuracy package. So everything you see in the image that is blue is going to be chilled. So some of this is standard, like your spindle, your torque motors, your drives. But when we add this package, we also start cooling the linear rails themselves for the X, Y, and Z, just an effort to keep everything stable. So with that, we're going to get into the demo video of the knee. So first off, like I had mentioned before, we're starting from a block, which is not going to be typical for this type of part, but we'll do the trick for today. So we have a lot of material to remove along the outside to get it to that near net shape. Also on the inside, there's a lot of material which we have to get out. And here we're using a 1-inch high feed indexable cutter from Walter.
Yeah, I really like the idea of starting the roughing process with a high feed mill. It's a really efficient way to get a lot of material away quickly. But here we're looking at that 4-flute titanium series tool. So as I mentioned, you're going to see a lot of different configurations of the same geometry being used on this part today.
Toolpath wise, in this situation, we're using a combination of our optimized 3-axis roughing as well as some 2D toolpaths. So that strong base of software, not just 5-axis, not just barrel cutters, but general toolpaths as well. Collision checking against the machine, the tool, the fixture, the holder, everything for process security throughout.
Here's another version of that 4-flute titanium series. As I mentioned, the tool design has an eccentric relief on it. So that's going to provide a very strong, stable cutting edge when you're in this difficult to machine titanium material that usually generates quite a bit of cutting force pushing back on that tool.
At this point, we're going to switch to our max roughing toolpath, where we're using a tricoil style cut to clear out the slot in the knee itself. You see all the chips, a lot of material removal, quicker material removal, highly dynamic. Here we're using actually the same cycle we use with the barrel cutter, but we're using it with a standard end mill.
You'll notice a lot of the repositioning moves, or all the repositioning moves, once we're in the cut, are staying right up against the part. So we're repositioning at 5-axis, which is very dynamic with the tool path and the machine. And also, we'll look at this 5-axis swerf cut on the outside of the part here. We'll be able to take a pretty large step down while still being very close to the final surface. So we have a very consistent semi-finished pass, which is going to be critical for having an accurate finish.
Here we're switching to finishing. We're using a ball mill to finish the sides, just like we did in our last example. Making sure there's a smooth transition from the sides to the condyle surface, the bearing surface of the knee. We don't want any burrs or inconsistencies in the surface from the transition of those two surfaces. Now we get to the barrel cutter. So you can see it's a fixed inclination with mostly C-axis motion, and we're going to work our way up the surface, making sure it's nice and smooth. Climb milling as we go, which is always preferred with a barrel cutter. Very good motion on the GROB, nice and smooth. And of course, good chip evacuation as well.
Here we're, again, coming back to the 4-flute titanium series tool for doing some of the finishing applications. Again, when we did the finishing with the MD838, keep in mind that that is the conical version of the barrel cutter and not the tangential. There is a difference in the application between the two and the capability of both different styles of barrel cutters.
So lastly here, we're looking at doing all the fillets and blending on the outside of the part. And we're actually using a barrel tool, but using the end, which is a diameter 4. So still makes for a very stable tool using a barrel for that application. So at the end here, you see everything's finished. We have one part roughed, the other part is finished. And now we're able to do the part off. And now some images to show the finished part. So with that, we'll see if we have any questions that came in and do our best to answer those.
Okay, so we have had a few questions come in, and if we do not get to yours, we will answer after the webinar. So if you do have questions and you haven't entered it yet, please feel free to. The first question is for Walter. How do I get some of those tools to try, particularly anything that Walter considers special, like a custom MD838 tool?
Yep, thanks for the question. We do sell through distribution, so you would have to contact one of our authorized distributors or our local Walter FSC, and they would help the order process and get you that special tool.
Okay, there's another question for GROB. How has GROB machined any other implant type parts?
Sure. So in the past, we've had larger machines, so we've done more medical device manufacturing. We have done some projects. One in particular comes to mind on the hip stem, where we actually did it everything from the cone to the tip in a single operation. And we had done that by using our table with a tailstock. So we supported everything on the top when we could do everything in a single operation. So yes, we've done several applications specifically here in Bluffton on the medical side, and worldwide we have quite a bit of experience in joint effort with our headquarters.
Okay, we had a question for Open Mind. Why not just use a tapered tool instead of a barrel cutter?
Well, you could use a tapered tool. Of course, you're not going to have a very good surface finish. The reason for that is if there's any inconsistencies in the tool length via just measuring it or thermal growth in the machine or whatever the case may be, you'll actually see gaps between, or not gaps, but differences in the tool paths as it goes through the surface. You know, with a barrel cutter, it's essentially just like a big ball mill. So really all you're getting is a scallop height. and and the other thing is, you don't have control of the contact point like you do with a barrel cutter. So you have a fixed contact point, no matter what the situation is. It's always on that angle. It's like I said, you could do it, but a barrel tool is a much cleaner, much smarter solution.
Okay, another question came in for OpenMine. Does using a lens cutter make sense in this application?
Yes and no. I'd say it's better than a ball mill. Of course, with a lens cutter, you're really limited to the radius on the tool itself. So typically, a barrel cutter has a cutting radius of anywhere between 10 to 20 inches, even more, 50 inches radius. So you have a much bigger cutting radius, therefore a smaller scallop height. The other thing with a lens cutter, you're always fighting to stay off the tip of the tool. Anybody who's ever cut with a ball mill on the tip knows that you're not really actually cutting, you're just pushing material. Where with a conical style barrel cutter, you never run into that situation because you're always cutting on the side of the tool.
Okay, we're running a little low on time here, so we're going to answer one more question, and this one is for Walter. Where do I get speed and feed information for the Walter tools?
Great question. We do publish speed and feed information in our catalog, but actually what we find more convenient is to use a product that we call Global Product Search, or GPS. You can access it right on our website, and it's our tool finding software, but it also provides feeds and speeds information as well as torque requirements, cost per part, tool life, and a lot of other information that you might find useful when either executing your machining strategy or even planning your machining strategy. And as I mentioned, you can get that directly on our website.
All right, that ends it for this webinar. So thanks everybody for your time and listening. And if you have any questions, you're always welcome to reach out. Our contacts are here. You can reach out directly. And for those of you who didn't get to your questions, we will be reaching out shortly. Thanks.